Okay, in the second half of first chapter, we will touch about more on the uh, energy law, thermodynamics law, gas law, centrifugal and latent heat, and the last is enthalpy. Okay, before I will start uh, the class. I would like to make sure you can hear me clearly. Okay, class, you can hear me clearly. Can you? Anybody can answer? Anybody?
Sir, tak dengar sir.
Oh, tak dengar. So what I have to do, I will like to close the camera. I will change the camera as the microphone. So how about the now? You can hear me? Hello? Can you hear me? Hello? Okay,
Yes.
not?
Yes sir, yes sir.
Yes, yes.
Can hear, sir, but not clearly.
Oh, cannot clearly, eh? Cannot hear clearly. Also, what I can to do now? So I have no idea right now. Mm, okay, I actually already adjust setting in the maximum of sound. Okay. How about now? Test, test, test. Can you hear me? Can you hear me?
Yes.
Okay, okay. So, how about the slide presentation? Feasible from your side? Huh? How, how about the slide? Is it visible?
The slide is visible, sir, but sir still not clear.
Yeah, I have no idea to set up this. Uh, Firstly, I would like to make sure the sound is very clear. Already setting all maximum. Okay. Okay, I hope I can run the class. Yeah. Uh, and then I will share the video with clearly sound you can hear. So I will upload in the Ulearn, so you can check there. But the first, because I already make schedule in this class, so better I will start the class. Yeah. Okay. What we have to achieve today, we have several objectives. Yeah. The first, explain the basic concept of the thermodynamics, such as a state postulate, equilibrium process, and cycle. The second is introduce the concept of energy and define its various forms. And the third, discuss the nature of the internal energy. And the last is define the concept of heat and the terminology associated with the energy transfer by heat. Okay, now we go to the thermodynamics and energy. So many terms will be related to the thermodynamics. Yeah. So I would like to introduce first the thermodynamics itself. The thermodynamics is the science of energy. So the energy ability to cause change. Yeah. So the name thermodynamics stem from the Greek word therm as heat and dynamic as power. The conservation of energy principle during an interaction energy can change from one form to another, but the total amount of energy remains constant. Energy cannot be created or destroyed. Yeah, the first law of thermodynamics, an expression of the conservation of energy principle. So actually, the conservation energy is related to the first law of thermodynamic, yeah, because the energy cannot be created or destroyed, yeah. So the first law said that energy is thermodynamic property. Okay, after that, we go to the second law of thermodynamics. It asserts that energy has quality as well as quantity. Actually, the second law of thermodynamics will relate to the efficiency. Yeah? After we try to utilize some energy in the our device, it's a certain device. So then we try to calculate the efficiency. So this second law will relate to the uh, 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 efficiency. Yeah, efficiency. So classical thermodynamics, we'll discuss about the macroscopic. Yeah. To the study about thermodynamics doesn't require knowledge of the behavior individual particles. So we don't go to into the particle itself. So just a touch on the surface of the kind of the thermodynamics. Yeah. Such as energy. Yeah. So we only talk as general. When we go to the in such a microscopic approach, it means we in the statistically thermodynamics system. So example, we try to learn about the internal energy. Yeah? So as we know, we have a kind of energy or fuel from the fuel. So if you go to commercial fuel from the petrol station, we will find RON 95, RON 97, RON 100. It means will bring the internal energy is different, yeah, from the 95, 97 is 100. It means this kind of energy is related to internal energy, yeah, internal energy. Okay, now a form of energy, yeah. Okay, actually we are already touched about the macroscopic, only on the surface of the energy, and also microscopic form energy, yeah. Like internal energy is considered as microscopic, yeah. And then kinetic energy is a macro, and potential energy is also macro. So the total energy, yeah, is sum of them: internal energy, kinetic energy, and potential of energy. Okay, this kind of sum equation from the energy form. So we check first in the kinetic energy. So kinetic energy will be related to the motion. So should we have velocity of the mass. Yeah? So when we try to find the unit in the energy only, so we should be uh, times to the mass. But when we need the energy per unit mass, so it means the mass will be height. So we will put on the unit. Okay. So when we times to the mass to the energy, so we come to energy only. So both kinetic and potential energy, we can use this form of the uh, equation for formula energy without include the mass. Okay. Okay. This type is for the energy form, and then when we go to the uh, other calculation in the system, piping system, tubing system, duct system, will be related to the quantity of the air, mass flow rate, anything. So mass flow rate will be calculated by m dot on the head. So will be calculated by rho v dot. V dot is actually yeah uh, uh, AV, AV. A is area, and this V is velocity average. So V dot is mean velocity rate, velocity rate. And for form of energy, we can rewrite by E dot, mean energy rate, energy rate per second. So every second, like the watt, kilowatt is considered is energy rate, and if you use joule, it will be a per second. So per second is mean watt. Joule per second is mean similar to watt. Kilojoule per second is mean similar to kilowatt. Okay, this one is total of energy. Total energy is sum of various form of energy. So internal energy is U, kinetic energy is Ka, Ke, and then potential energy is Pe. Okay, this one is another type of energy per unit mass. We can use small letter, but the unit is energy per mass. Okay. Okay, this one is energy balancing. So if one system we try to input the energy, and then the energy out should be similar to energy in. So it's one we call energy balance. So if we supply the energy in one system, okay, take a look into the figure 2.45. You can see the supply energy from the thermal energy, and then mechanical energy, and then the total should be calculated by like this. So because of E energy in equal to energy out, so that's why the equal to E system. Okay, actually when we're talking about the balancing, E in negative E out is a something energy work in the system. Okay, this one the mechanism of energy transfer, E in and E out. So kind of the total energy, maybe out another form of kind of energy. So if we try to supply with the mechanical energy, but maybe come out with the thermal energy, not only energy in kinetic or potential, but maybe can be in the thermal energy. Okay. This one is balancing energy, with the variant of form energy. So if we consider the total sum of energy involving thermal, mechanical, and then this one is another type of energy, EMS in and EMS out. So the total is E system. I mean the balancing is E system. Okay, now we go to other term will be frequently used in the hatchback system. So this one is come from the thermodynamic system to explain the condition certain system. So in the case maybe we analyze in the one building as a one system or one room as one system. So we will relate to the hello. Sorry, apa tu? So consider us uh, this minute to make our class going smooth. Okay, then this term will be taught in the certain condition. So the system is quantity matter, a region in space chosen for study. So like I said previous just now, we will create one system can be in the space like the one room or one building, considered one system. And then outside of the system, we call the surrounding. Okay, whatever from the outside, like the mass and energy, we call the surrounding. But separating within the system and the surrounding, we call a boundary. So we will close with the boundary. So boundary will be considered fixed or movable, closed or open, depend on the study case. Okay, a closed system, a fixed amount of mass and no mass can cross its boundary. So when we consider the system is closed, no mass can be crossed to outside to surrounding or to the system. Okay, but open can do that, so can cross the boundary. So mass can be come from outside surrounding into the system, and vice versa from the system can be crossed to the surrounding. The control of surface, the boundary of the control volume, it can be real or imaginary. So sometimes when we create the system, sometimes will be uh, uh, what will be closed by the boundary, real boundary, like the solid boundary. Yeah. Sometimes we make like imaginary. Imaginary is like, as we know, the turbine system, actually the mass can be come to turbine, turbine system inside, and then the mass can cross to the surrounding. So within the indoor, and outdoor the system, enclosed by the uh, imaginary boundary, imaginary boundary, because no window there available in the system, no door also, so close by the imaginary. But the condition is different. Inside the system, already in the certain pressure, temperature, anything, but no solid boundary. Hey, let me see. Okay. Okay, we proceed to properties. These properties actually familiar with us in the thermodynamic system, with the properties of M as mass, V with volume, T, and so on until to density rho. So properties, property itself is any characteristic of a system. Some familiar properties are pressure P, temperature T, volume V, and the mass M. So from there, from the list of the property, we can divide by extensive and properties and intensive properties. Extensive, and intensive. So extensive will be expand. The properties will be expand in the size. So consider as extensive, like the mass can be expand, and volume also can be expand, but the temperature, pressure, and density cannot. So we call the intensive opposite of extensive. Specific property, extensive property per unit mass. So after we make like the energy as unit, but we try to calculate per mass condition. So that we call the specific properties. Okay, this one another condition in the system. So actually this system, this one is fundamental before we go to the hatchback system. So why we consider the system is equilibrium, thermal is equilibrium, mechanical equilibrium, phase equilibrium. Actually much terminology come from the thermodynamic system. For example, we to explain the condition, the state is balanced. It means the equilibrium, thermal is equilibrium. Okay. So where is the thermal equilibrium? The temperature is the same to the entire system. So if we try to make entire room in the certain temperature condition, mean the temperature, any corner, any position, any space will be give information in the same temperature. Okay. Phase equilibrium involving two phase, and when the mass is phase reach the equilibrium level and stay there. So phase equilibrium is mean if we consider in the liquid, so will be consistent in the liquid and that condition, always in that condition. And chemical, so the molecule content will be similar, like the water always H2O. So it means chemical equilibrium still there. If we change to the gas, so it means no more in H2O already changed. Maybe already create the gas by another kind of the molecule. Okay, in the ideal gas, we will touch the equation about the PV-MRT. Actually, this type of energy can be changed, can be accurate with the other form of the equation, like PV-MRT can be okay. V actually will be represented by two conditions. Yeah? V is not always volume. When we mention the V with the capital V letter, it means volume. But V in small letter, it means specific volume. Okay, this one is different. Different also unit. So actually, V for the specific volume is per row. Row is per density. Row is mentioned to density of the mass. So if we consider small v as per row, so we will change the condition of the equation in the ideal gas. So no more in PV equal to MRT. We can rewrite by other form of the equation like the P rho equal to RT. Okay. I hope you understand what I mean. Okay, this one is similar condition of the with the this one is balancing mass balancing. Yeah, so mass in is equal to mass out. So whatever we supply to the system, so mass, yeah, for example like air supply in the building or room from the ecosystem. So for the inlet, so as the return of air mass will be similar to the air supply into that room. Okay, this is similar to the equilibrium of energy. So the mass also will be similar with whatever supply to the mass, number of quantity of mass in the system will be returned by similar number quantity of the air to return. Okay, this one is another form from the ideal gas equation, PV-MRT. Now the mass where we carry it out come out with the M as a mass. So the formula we change like this. So when the system in certain condition in P1 V1 over T1 equal to P2 V2 per T2. This means M1, this one is M1 and this one is M2. So M1 will be equal M2. Sometimes maybe P1 is lower, but this one will be balanced by P2 is higher, but temperature is lower, higher also, and then the V2 is maybe different, but the total will be similar to total in the condition 1. Yeah, this one. Okay, this one is another form of the ideal gas equation. So R mentioned to the air constant. So if we consider is outside air, like the environment air, so the air will be get the constant number. So we can get this number from the table. Okay, this one we go to sensible and latent heat. So this is will be common use in term of HVAC system. So we will be used in latent heat official, latent heat of evaporation. What condition actually is it? Yeah. So this one is to describe the condition of refrigeration system. So actually, refrigeration system will be changed, from the phase condition in the liquid and then change to the gas, vapor, and then what energy to change. the quantity, what the quantity energy need to change to phase, to other phase, from the other phase condition to other phase, from liquid to the other kind of the phase like vapor or gas. So why this happen? Because we need refrigerant in that condition of phase will be supply the kind of the energy. So the energy we will supply to the environment, what kind of energy, and then what kind of the phase, and then to the indoor room itself, inside of the room, what kind of the phase, and then how much energy. Okay, we go to the latent heat definition. The latent heat, the definition, the amount of energy absorbed or released during a phase change process. So when we try to change the energy, the phase of certain compound, so we need energy. So when the energy change, the change phase, so we call the latent heat. Latent heat. Latent heat fission. This is more specific. This one is energy absorbed during melting. Okay, when we try to change from the solid into the liquid phase, so we call the fusion, latent heat of fusion. So when we change from the liquid to the vapor, so we call this one is latent heat of vaporation. The amount of energy, relate to energy. It's not about the temperature, but energy. Q, Q. So at 1 atm pressure, the latent heat of fusion of water, we need 333.7 kilojoule per kilogram, and the latent heat of the evaporation is 2000 to 156.5 kilojoule per kilogram. So higher when we try to change from the liquid into the vapor, because what we need is energy to separate molecule into the gas. So that's why we require the energy higher compared to the change to the from the solid to liquid. Because of solid, we only make bonding within the molecule. Bonding is a weakness only. It's just release the bonding, as we know in the solid will be bonded by higher bonded. It means the hardness bonded, but only release the bonded and then become the liquid. So the energy is not much compared to the when we try to evaporate evaporate the liquid. Okay, this one is based on the saturation temperature. This one is water, I think. This one is related to water. Yes, correct, water. Okay, now we go to formula or specific latent heat of fusion. The specific latent heat of fusion is solid is defined as amount of heat energy required to change 1 kilogram from solid to liquid or vice versa without any change in temperature. Okay, so hence the formula LF equal to QM, or we can rewrite by find out the Q by equal MLF. And then this one is formula for vaporization. latent heat of vaporization, LV. So the specific latent heat of vaporization of liquid is defined as amount of heat energy required to change 1 kilogram liquid to vapor or vice versa. Okay, solid to liquid. This one is a energy of in the water system, from the ice to the liquid. Okay, solid to liquid energy is needed to move molecule slightly further apart so that the attraction between the molecule is weaker. So what I said just now, we just remove the bonding within molecule, and then become the as water. As we know, the solid we will good range of molecule because of bonded each other. So when we try to weaker of the bonded and become liquid. Now the molecule can roll and slide after we change the phase. So molecule now become moving from the molecule to other molecule. So no more bond to each other. Liquid to gas energy is needed to separate the molecule against the mutual attraction. Actually, this one is a higher of bonding within the molecule. So attraction within them, we try to separate within them. So for example, H2O, we try to remove H2O, become H itself and O itself. So this is a need higher of energy. This is why LV is larger there. Yes, correct. Okay, we go to saturation condition. So actually when we plot the P as pressure and time, temperature, or we can plot P with the specific volume. We can get like this. So the this part, the left part, is actually saturated liquid of water, and for the right side of the saturated will inform saturated of vapor condition. So within them, within this saturated liquid to saturated vapor, so will be a mixed condition within the saturated vapor and saturated liquid, depend on the condition mixture. Sometimes when we go close to the saturated liquid line here, maybe portion of liquid is dominated. When we go to the other side, close, maybe close to here, here maybe around here. So the condition mixture is dominated by a vapor condition. Maybe 50% is maybe exactly within symmetry within the saturated line of liquid and saturated line and of the vapor. So will be around here. So will be 50% condition of mixture. So the mass total is combined mass of the fluid and mass of the gas inside here. And then the X itself is mass of vapor compared to mass total. So mass total, consider this one, combination liquid and vapor to vapor, mass of vapor. So X itself. So if we consider one is mentioned to the vapor condition. If the X is 0, it means totally in the 100% of saturated liquid. Okay. Okay, this one is other type how to find mixture condition by involving the enthalpy and internal energy. So we can use this formula. Okay, I don't touch much in this kind of the formula because this one is already discussed in the thermodynamics. So this one is portion condition, yeah, of percentage by percentage within mixture within the vapor and then the liquid, yeah, condition. So maybe composition nitrogen is higher. Composition is can be vapor can be reached at 78 percent, oxygen, argon, and so on. Okay, I need to take 5, yeah, before I continue to the next slide. So I need to check the attendance inside here. Okay, we have 85 number of participants. So I need to download. Okay, already there. So who else to ask me to join? Where is someone asked me to join? Yeah. Okay. Anybody want to ask before we go to proceed to next slide? Anybody want to ask me? Hello?
Setakat ni tak ada.
Okay, tak ada ya. Where is the... Oh, yeah. Oh, yeah. Muhammad Iqmal, can you join? Muhammad Iqmal. I want to invite Muhammad Iqmal back. Not sure, cannot.
Sir. Hello.
Hello.
Muhammad Iqmal couldn't join since just now. He said that you can only hear, sir, but not the slide. He can't see the slide.
Oh,
Dia kata network ada problem.
He got an internet issue.
internet issue.
Tak pergi dia nanti nak tidur rumah. Ha? Jadi dia. Malam 13 dah tu kan? Benda ni dia tadi. Dia mesti macam kalai.
He said it's keep on saying sorry we couldn't connect. Sir, hello.
Yeah, hello.
Iqmal said that he keep on getting an error message saying that sorry we couldn't connect.
Like that. Okay, I try to continue the slide presentation in the second half of chapter 2. I hope you still feasible to access my slide. Okay. Can you see me? Can you see my slide?
Yes, sir.
Okay. Okay, this one is properties of the dry air. Actually, dry air will be give some parameters to reading, like molecular weight, yeah, gas constant, specific volume, specific heat, enthalpy. Yeah, so will be give some information from the several parameters, so we can measurement this condition in the dry air. So actually, the dry air will be present by molecular weight 28.9 gram per mole, and the specific heat and gas constant dry air, so and so on will be already tabled actually this condition, so you can get this information from the Google also, some from book, yeah. And then this condition of properties when the condition water in the vapor. Okay, and then this equation within air and vapor mixture condition. Yeah, we can use Gibbs-Dalton law. Yeah, jadi the total is air, dry air with the wet air or mixed condition. And then we go to the condition dew point temperature. Actually, uh, yeah, as we know, we try to condition the air with the hatchback system devices. So actually, anything will be related to the air, to the water condition, because air will be related to the water condition. And sometimes we also use refrigerant in some hatchback device with the water, not only refrigerant from the chemical kind. Yeah, so that's why we try to uh, create understanding more in the water and the air system. Yeah. So the dew point temperature is the water vapor in the air will be saturated. When air is at the temperature equal to the saturation temperature corresponding to the partial pressure exerted by water vapor. So this temperature is called dew point temperature. So when the dew point condition, the pressure of saturated also in that uh, area mentioned in the condition pressure saturated with the content of water. When the touch the solid medium and then become to condensation. So that's why sometimes in the morning we feel condensation on the leaf, and grass, anything. Some in the if we park our car in the outside, so we will feel wet because of condensation. The pressure of the with the temperature become to the condensation. Yeah. Humidity ratio. Okay. Actually, this condition we will describe the condition of the space. So that's why we try to learn what condition actually right now, and then what the condition we will try to we achieve. Yeah, we try to achieve that in the temperature, in the pressure, and also in the moisturization system condition. So that's why we try to measure certain condition of the space relate to the air and the water condition system, because relate to the what the controlling system of the space. So humidity ratio is the ratio of weight of the moisture to the weight of the dry air in the air vapor mixture. So we try to describe the condition of the space. How about the condition in this space? How about condition in our room? How about a condition right now we want to control? What the condition? So we will measure in certain parameter. Sometimes we measure with the humidity ratio. Sometimes we measure with temperature. Sometimes we measure with relative humidity. So we will use this relationship, to control the room. So this is ideal gas equation, as I mentioned before. So the comparison ratio of humidity ratio is comparison within the mass with the wet to the dry air. So we can use this comparison. We call humidity ratio by W. So humidity ratio is represented by capital W. This one pressure, total pressure is total pressure of W is mentioned to humidity, and then the air A is dry air. So this one we can use the final of formula for humidity ratio. Okay, this one relative humidity of equation. So relative humidity is the humidity ratio of the air expressed as percent of the total saturation point for that specific temperature. So relative humidity also we will use to measure this parameter, to measure condition of relate to the human comfort also. This one is the formula. Humidity heat, is amount of heat required to raise the temperature of 1 kilogram dry air plus water vapor present by 1 kilo. Okay, specific volume of the dry air plus water vapor in the air. So sometimes we also measure in this condition certain condition of the air with the specific volume. Okay, maybe later on I will show how relate to the condition of the air by using graphic. Okay, we try to understand first the term that we try to measure to condition the certain condition of the room, of the space. So we also measure the wet bulb temperature. Actually, the wet bulb is common use in the temperature, room temperature measurement. The wet bulb temperature is the temperature read by the thermometer cover in water socket cloth, wet bulb thermometer, over which air is passed. So we will cover with the socket cloth, and then we try to measure the air through that socket, socket water. And then the formula, this one. Okay. Now, actually, all of parameter that we measuring refer to one graph. This graph is we call what? Psychometric chart. Psychometric chart. So if find dew point temperature, humidity ratio, humid volume, and relative humidity of air having a dry bulb temperature. So we have input from the space is temperature 40 degrees Celsius and wet bulb temperature is 30 degree Celsius. So when we measure the room, so from there we go to the psychometric chart. So we come out with several information from here. Certainly, this one is sensitive, very sensitive, because we try or check with the eye only. So the skill is from the eye. So if you make a mistake, in your eyes, so will be get the inaccurate result for a certain condition parameter measurement. For example, this one with the curving line is RH, relative humidity, and then you can see here with the longitudinal, sorry, this one is horizontal, horizontal line. Mention about the humidity ratio here. You can see here, and then also in the vertical line here, dry bulb. You can get other information like this. Specific enthalpy, you can get information. So by given in the problem is 40 and 30, you can check here. So just denote the number 30 and the 40. So we can get any information here. Like this is RH, RH relative humidity with curving, and then anything will give information. So we can check here in the 30. This one is the temperature. This one is the number is not mentioned, but we can get the temperature for dry bulb. Okay, we can see here, but this one humidity moisturizer, humidity is kilogram per kilogram. If you change to the gram, you can get the big number. We try to get the in the gram. This one in kilogram. Okay. This one is just introduce how to use the psychometric charts. So we will come out with the dry bulb with a vertical line, and also wet bulb with the certain angle here to maybe in the 45 degree or something, and the relative humidity with curving and dew point here. Okay, humidity ratio in W just now comparison, so we can check. Specific enthalpy. Actually, this one is outside of the graph that I mentioned before. Enthalpy is also have the line here. We mentioned the data, and this one is specific volume. So from one chart only, so we can get any information. So be careful in the psychometric charts. Make sure chart is appropriate for your environment. Figure out what two quantities you know. So if you try to meet two line, to make sure we have two parameters to given information, two quantities, then understanding the slope on the chart, find the intersection. The intersection is very hard to find because sometimes we meet in intersection, but sometimes we try to get from the calculation because the line is not mentioned in the chart. So what we can do is probability ratio. So now we go to one example. As I mentioned before, we should be collect two parameter to create the intersection. Yeah? So the first temperature of the dry, yeah, in 25 below, and then temperature of the wet, yeah, wet bulb. So we can meet here wet bulb, and then after that intersection in the this one is pink, yeah, pink color is RH, and then what else? The blue one is just now. I think. I forget what this. Maybe we can check in the psychometric chart, yeah. What the line, and then all information will be collect here. So anything will be informed. So what I understand just now, enthalpy is around here. Maybe 57. Yes, 57.5 is enthalpy. So never mind. If we use directly psychometric charts, so we can carry out the all parameter, but difficult in the slide to use this should be mentioned this one the what properties, so you can know but you can cross check, so you can compare to the graph what information is actually. Okay, sensible heating or cooling, a psychometric process that involves in increase or decrease in the temperature of air without changing its humidity ratio. So example, passing moist air over a room, space heater, and clean air over the heating coil. So we can measure the condition. So when we measure not only in the space, but also in the pipe system itself, duct system itself. Yeah. So when we can go to clean when the output passing, output air passing to the duct, so we can measure that part. Okay, this one you can measure the condition in the duct system, what happened and how much, the quantity, all information. So sometimes we can control this one is moisturization, humidity ratio. We can control by increasing or even increase the temperature of the dry bulb. So we can maintain the humidity ratio. So not only increase the temperature, but also we can maintain the. So that's why we try to make the condition will be in range, in range of human comfort. Maybe in the two enthalpy already increased, but humidity ratio is still there. Okay, now one example. If we try to control the room, with the T2 is 60 degrees Celsius, and then the ratio, humidity ratio, 50 degrees Celsius, and then the relative humidity 58.8%. So T3 is 70 degree. And how about the ratio, humidity ratio, and relative specific? So you can go to the psychometric charge. So we come out with the uh, unknown parameter. This one, PW3, humidity ratio 3, and then relative humidity 3. So from 50 to the 70. So the the first answer is 7. This one is 70 to 55. 55 degree Celsius. So this one is 55. 51. Sorry, 51 degree. Okay. Then RH this one is become 70. 70 37.6 percent. 37.6%. So that's how we measure the condition with temperature change. Yeah. So heating and humidifying psychrometric process that involve the simultaneous increase in both the dry bulb temperature and humidity ratio of the air. So if we increase the certain condition and simultaneous increase the temperature and humidity ratio. Okay, then we go to a last example before I close the class here. 2.5 cubic meter of lumber is being dried at 60 degrees Celsius dry bulb. Temperature is 52 degree wet bulb temperature. The drying rate of the lumber is 12.5 layer of water per hour. If outside air is 27 degree. Dry bulb temperature and 80% relative humidity. How much outside air is needed per minute to carry away apparent moisture? Okay, this one the answer, the position in psychometric charts. So actually psychometric charts we will learn in deep by practically in the lab. Actually this one is related to lab 4. If not my mistaken, we will learn indeed on the lab 4. Okay. And then we can measure the differentiate, what differentiate between the first condition and second condition, or HR, flow rate condition, yeah. And then this one is condition, H condition of the point 1 and point 2. Okay. Okay, that's all lecture class for today. If you need something or discussing or question, we can discuss right now before I close the class. So anyone to ask something? Hello class? Anything? No? Muhammad Tajuddin? No? Okay. Good time. Thank you, Muhammad Tajuddin. This one also with Tam. Thank you. So, Ahmad Farouk. Okay. If you don't have any question right now, maybe we can discuss in another day or another time using and WhatsApp group, WhatsApp or another kind of platform. Maybe you can send me email or anything. So never mind. If you don't have any question right now, so we can close the class. Yeah. Okay. Thank you all. Thank you for your attendance and thank you for your whatever lah. Thank you. Assalamualaikum and good afternoon. See you next class.
Thank you, sir.
Thank you, sir. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.